All right, perfect. Okay, welcome everyone to the March 2022 TEPS seminar. Today we're going to have three TEPS trainees give presentations. We have Keavin Moore from McGill, Charissa Campbell from York, and Joshua Hedgepeth from the University of Western Ontario. Keavin, we'll have you go first. And Keavin, your supervisor, I know is Nicholas Cowan, who's unavailable, so I'll give your introduction. I'll do my best here not to butcher anything. So Keavin Moore is a fourth-year PhD student in the Earth and Planetary Sciences Department at McGill University, working with Nicholas Cowan to model and predict the habitability of Earth-like planets orbiting M-dwarf stars. Previously, Keavin obtained his master's in physics and astronomy from university in 2017, working with Ray J on circumbinary planets. Keavin hopes his research on habitability will contribute to the exciting and ongoing search for extraterrestrial life. All right, Keavin, take it away.
All right, I think I'm good. Cool. Okay, hey everyone, I'm Keavin Moore. I'm a fourth-year PhD student at McGill, working with Nick Cowan, and my research involves trying to determine the surface water inventories of Earth-like planets orbiting M-dwarf stars using computer modeling to try and predict their potential habitability based on the presence of liquid surface. So for those of you that are unfamiliar, M-dwarf stars are the most common stars in our galaxy. They're much more common than G-dwarfs like the sun, but they're much smaller and much less luminous. And because of their very small size, orbiting planets orbit much, much closer to their host star, and the habitable zone, so the region where liquid surface water can exist, is much, much closer to the star. So in this image, you can see, I'm not sure if you can see my mouse, but the orbits of all 7 TRAPPIST planets are far within the orbit of Mercury within our own solar system. So these planets are orbiting very, very close to their host stars compared to the solar system planets orbiting the sun. And because they're orbiting so close and M-dwarfs are extremely active stars, these planets are being bombarded by radiation across all wavelengths. But in particular, we're concerned with X-ray and ultraviolet radiation, which is collectively known as XUV radiation. Now, this XUV radiation is important because it impinges on the atmospheres of these orbiting rocky planets, and it can photodissociate water molecules high in the atmosphere and drive loss to space. This loss can be very significant, and it can even lead to complete desiccation of the surface of these planets, which would be obviously a negative for habitability based on the presence of surface water. So for the rest of this talk, I will refer to an Earth-like planet orbiting an M-dwarf star as an M-Earth. Now, Earth is very unique in that it is the only planet we know that has active plate tectonics. And so because Earth has these active plate tectonics occurring, it is able to cycle water between the surface and the interior. And so while most people are familiar, well, everyone is familiar with the fact that there's an ocean worth of water on the surface of the Earth, you may be surprised to find out that there's actually multiple oceans worth of water sequestered away in the interior of the Earth within the mantle. And so because of that, it is able to cycle between these two reservoirs on geological timescales. And so this is kind of a complicated figure. So I just want to point out the two upwelling and downwelling limbs of this deep water cycle. So on the left, the water is degassed from the mantle to the surface through mid-ocean ridge volcanism. And at these mid-ocean ridges is also where new crust is created. And so this crust is created at the mid-ocean ridge, and then it begins traveling. It's pushed towards the subduction zone, you can see there on the right. And as it's traveling towards the subduction zone, its structure becomes hydrothermally altered, and it incorporates water into its molecular structure. So eventually this hydrated slab is forced back down into the interior of the Earth. And while a lot of the water will boil off and contribute to these subduction volcanoes you can see above, some of the water will continue from the surface back into the interior. And so water is regassed from the surface into the mantle, and so that really completes the deep water cycle. So we wanted to take this model of the Earth's deep water cycle and apply it to an Earth-like planet around an M-dwarf star, with this active plate tectonics allowing this deep water cycling, and also allowing this loss to space, the loss of water to space, because these planets are very susceptible to losing substantial amounts of water to space. And so we created this very simple 2-box model to allow the simulations of the deep water cycle with loss occurring from the surface. So the 2 boxes are just the surface reservoir, which contains the liquid ocean and the atmosphere above it. And the interior reservoir is the mantle where water can be regassed back into it from the surface, but it's not available to be lost like it is at the surface to space. So as far as we were concerned, looking at this very simple two-box model, we were saying a planet is habitable as long as it has some liquid surface water present. However, planets start out very, very hot after formation. And one of the reasons is because the host star, so the host M dwarf in this case, is outputting a very large amount of radiation, which is hitting this planet. And so there's a limit to how much can be efficiently radiated away to maintain a surface temperature before the surface temperature runs away, as you can see in this figure. And so if the incoming radiation is above what's known as the Simpson-Nakajima limit, then the surface temperature very rapidly runs away into these very high values of surface temperature. And this is not only important because it means all the water will have evaporated and be in a, but it's also important because the solidus temperature of the Earth's crust, so the temperature at which the crust will melt, is in the range from about 900 Kelvin to about 1200 Kelvin. And so on this diagram, you can see these runaway greenhouse temperatures are much higher than that. And so instead of having a steam atmosphere above a solid surface, we'll actually have a steam atmosphere above a molten surface during this early runaway greenhouse stage. And in fact, this M-Earth will actually begin in a molten state. This is known as the magma ocean phase, and it will be concurrent with this early runaway greenhouse phase. And it's not only due to the runaway greenhouse phase, there's also a substantial amount of accretionary energy that contributes to the planet being molten at the beginning as well. So essentially, we have another box model of this magma ocean phase at the beginning, where we have the magma ocean solidifying from the bottom up. As the mantle solidifies from the bottom up, a very small amount of water is sequestered away in the mantle. So I have the partition coefficient here, but essentially the takeaway is that as it solidifies at a given time step, 1,000 times more water will remain actually in this magma ocean than will actually be sequestered into the solid phase in the mantle. And so you can imagine as the magma ocean solidifies, a little bit of water is sequestered away in the mantle, but that will enrich the magma ocean with time. And so there's a point where the magma ocean becomes thin enough that it is saturated with water. And as you can see, the saturation limit is very high for water in a silicate melt of a magma ocean. And we have it set as about 10 weight%. So when 10% of the weight is water, it will be supersaturated. When this occurs, it is able to, the magma ocean is able to degas water into the atmosphere from the magma ocean, and it'll continue solidifying from there, and anything above saturation from that point on will be degassed into the atmosphere. So on this slide, I have at the top, I've specifically written energy limited loss. And that's because we can actually model two distinct regimes of loss depending on what stage of what evolutionary stage the planet is in at a given time. And so in this figure here, I show a very simple schematic for energy limited escape, which will occur during that early magma ocean phase. And as the name suggests, the amount of water that will be lost to space is limited by the amount of XUV radiation coming in. So remember, we have a steam atmosphere. There's lots of water readily available in the atmosphere to be photodissociated and lost to space. So the real limiting factor on the escape during this time is the amount of XUV radiation coming in from the host star. Now, once the magma ocean solidifies and we switch into that plate tectonics, deep water cycling I mentioned before, we switch to diffusion limited escape, which again, the name kind of hints at what it is. The amount of water lost to space is no longer limited by the amount of energy coming in. There's more than enough of that. It's now limited by the vertical diffusion of water through the atmosphere. And so we can account for both of these regimes as two different loss regimes, depending on the evolutionary stage the planet is in. And so this evolutionary path will not only depend on the time scale of how long the runaway greenhouse is, but it will also depend on how long it takes for the magma ocean to solidify itself. And so the interplay between these will kind of create two different paths that I show here. So after the magma ocean phase, if the runaway greenhouse phase is shorter or equal to the magma ocean phase, so the runaway greenhouse is over by the time the magma ocean solidifies, then we switch into this deep water cycling based on plate tectonics. You know, water can go from the interior to the surface, vice versa, and it can be lost to space. However, if the runaway greenhouse is longer than the magma ocean phase, then now we have to have this kind of transitionary box model before we can get to the plate tectonic cycling. And so the purpose of this is to just have water able to be degassed from the solid mantle to the surface. But this kind of negligibly thin magma puddle essentially prevents water from being brought back in from the surface back into the mantle before the plate tectonics occurs and subduction allows the water to be put back in. So I'll really quickly show some simulation results for this lower limb where the runaway greenhouse is longer than the magma ocean. So here we go. The length of the runaway greenhouse in this simulation is 56 million years. And during the runaway greenhouse, we'll have energy limited loss to space. And this left panel shows the length of the magma ocean. It solidifies in 50 million years. And you'll notice that I have this kind of weird, like reverse log scale on this panel. And that's because most of the action actually happens at the end. So I mentioned previously that water is very, very soluble in the magma ocean. And so it actually takes quite a long time for the layer to be thin enough that it's super saturated and actually able to degas water into the atmosphere. And so when that actually occurs, it very rapidly degasses all of the water that hasn't been sequestered away into the solid mantle, into the atmosphere by the time the magma ocean solidifies. So there's this little 6 million year time frame where we're still in a runaway greenhouse, still in energy limited loss. But then once the runaway greenhouse phase ends, the surface temperatures come down to a more manageable level, and the atmosphere condenses basically into an ocean, the steam atmosphere, and we switch to diffusion limited loss for the remainder of the simulation. However, the mantle, because there's so little water within the mantle during the beginning of this cycling phase, the mantle very rapidly becomes desiccated because the degassing rate depends on the mantle temperature high, although not as high as a melted magma ocean. However, that leads to desiccation of the mantle very rapidly. And so we don't really see cycling as we would expect using our cycling model itself. And so this kind of gives us the null hypothesis. Since the mantle is desiccated, there's no cycling, and as you would naively expect, water is just basically lost from the surface to space. So we think that there should be a way to sequester water away from this loss to space before that deep water cycling occurs. And our idea for that is by using what's known as a basal magma ocean. Now, in the basal magma ocean phase, basically you have the plate tectonic cycling occurring on top. So you have water degassing, water regassing, you have water being lost to space. But the basal magma ocean is gradually solidifying and sequestering water back into the solid mantle. And so we think this should be able to help with the problem of the mantle becoming completely desiccated and getting that very naive null hypothesis that I showed before. And so our idea with this is that the basal magma ocean should contain lots of water, since water is highly soluble in these silicate melts. And the solid mantle will contain a little water, as I showed before. And that once this basal magma ocean solidifies and we can switch into that plate tectonic cycling, the mantle will now contain some water instead of a very small amount of water. And that should actually allow some cycling between the surface and the mantle and allow some water to be hidden away from the loss and maybe help with the habitability prospects. But there's two unknowns in this basal magma ocean. The first is that we don't know how deep the basal magma ocean is going to be. So it could be on the order of hundreds to thousands of kilometers. And because water is so highly soluble in these silicate melts of the magma ocean, this is really going to determine the amount of water that can be stored away in this magma ocean, in this basal magma ocean, below the solid mantle. And the other unknown is that the basal magma ocean could persist for timescales of gigayears. So the initial magma ocean I was speaking about earlier lasted for about 50 million years, but this basal magma ocean lasts orders of magnitude longer. And because our simulations only last for about 5 billion years to kind of get an idea of the age of the Earth, just to apply that elsewhere, then the time scale of this basal magma ocean solidification will also be quite critical. So I did a quick simulation of this as well. This is the same simulation I showed before, but this time I'm allowing a basal magma ocean to hide water away below the solidified mantle. So in this panel again, I have that weird reverse log, but you can see the magma ocean is decreasing as it sequesters water not only into the solid mantle now, but also into the basal magma ocean. And there's still some water on the surface. And so once the initial magma ocean solidifies, the basal magma ocean now contains a pretty significant amount of water. There's some water on the surface and there's some water in the mantle. And so having this basal magma ocean exist for 2 billion years and just having it degas water, or sorry, solidify water and sequester it into the mantle at a constant rate over time will make this cycling obviously more interesting than it was. So the water in the basal magma ocean decreases with time. It actually goes through the mantle and then starts increasing the surface water content, which is pretty interesting. And eventually when the basal magma ocean ends, you lose water. But the important thing here is that the mantle doesn't become completely desiccated. And so there's actually a little more cycling happening here. So we're in the process of running a series of simulations for different host stars, different orbital distances, different magma ocean solidification timescales to predict the surface water inventories for a variety of planets. So stay tuned in the near future. Thanks for listening, and I would be happy to take any questions.
Can I ask a question?
Yep.
If I get this right, so water exists as like a gas dissolved in the magma ocean?
Yes, yes, it is dissolved in the magma ocean, exactly.
But it exists as a gas, right? It's like how oxygen is dissolved in like the ocean.
Yeah, I think that sounds right to me. I've never thought of it that way, but yeah, I think that would be it. Yeah.
So like, do you know like what's like the saturated amount of water in the magma ocean?
Yeah,
like so kilogram basis.
Oh, in a kilogram basis.
Like a kilogram of the mantle, the magma ocean and the mantle. Like how much water would you saturate?
Right. Oh, yeah. So we actually set that limit just to allow the magma ocean to solidify and degas, and we have it set as 10 weight percent. So when 10% of the weight of the mantle is water, then it starts degassing water into the atmosphere.
Right. And then so that would mean that there's more water in the mantle than there is in the surface, right?
More water in the mantle. No, because I showed that one figure where the magma ocean solidifies really quickly and degasses water really quickly because it's a very thin layer that it gets saturated because it's very highly soluble. So it's very close to the end of when the solidification is occurring that the water is degassed. So since there's so much still left in the magma ocean, because it partitions mainly into the melt as opposed to the solid, that when it starts degassing, there's so much water that it all just rapidly degasses up. So there's very, very little in the solid mantle, and it's mostly on the surface.
Oh, okay. All right. Thanks, man.
Yep, no worries.
Any other questions for Keavin? All right, well, thanks so much, Keavin, for the presentation. And up next, we have Charissa Campbell. So I will pass the figurative mic to Haley, Dr. Haley Sapers, to introduce Charissa.
Hello, everyone. I've had the privilege of working with Charissa over the last 2 years in Dr. John Moore's Planetary Volatile Laboratory. Charissa is a fourth-year PhD student in PBL working under John Moore's. She's been a member of the Curiosity rover team since first joining PBL in late 2016 and has continued to take a leadership role with the science team collaborators in John Moore's group. Charissa utilizes the onboard cameras, and she has investigated the Martian clouds and wind properties through various movies and observations. Charissa is now focused on determining any atmospheric changes compared to the InSight landing site, while also working in the lab on an optical meteorological station for Martian atmospheric studies. So I'll hand it over to you, Charissa.
All right, so thanks for the introduction, Haley. Thanks for coming to my talk. I am a PhD student with John Moore's. I also did my master's with John, so I've been with the group for quite a while now. And I'm going to talk to you about my main PhD project, which is MAPLE, a simple optical meteorological station for Mars. So a bit of a background into Martian meteorology. Mars actually does have 2 seasons: dust, which occurs during perihelion, during its closest point where it's warmer and creates local or global dust storms. And then the cloudy season, which is during aphelion when it's its furthest away, which creates colder temperatures and actually develops an equatorial cloud belt, which we have seen from the surface and orbit. So we have had a lot of Martian exploration to Mars to try to determine the atmosphere, aerosols that exist in the atmosphere. And as you can tell by this image here, it is actually easier to send orbiters than surface vehicles. And that is because you don't have to worry about landing, descent, and all that jazz. So it's a lot less time and money, which is unfortunate because orbiters, even though they do cover more area and they are not limited to driving constraints, they actually do struggle with seeing in the lower atmosphere about less than 10 kilometers. And that's simply because they have a larger error as they look through more of the atmosphere. So therefore, we are kind of missing that piece of data when it comes to seeing the atmosphere from the surface of Mars. From surface, we have actually been able to piece together certain areas of Mars based on what orbiters can't. As you can see in the blue circles there, that's supposed to represent kind of local conditions, as unfortunately we still have a question mark on the rest of the surface of Mars. And that kind of leads you to using Martian global climate models. And we must rely on these models to fill in those gaps that we can't see or utilize because we don't have enough surface vehicles on the surface and orbiters can't see that low. And it almost creates this feedback loop where the more data we have, the more accurate our models will be. And then the more accurate the models, and as kind of you need more data for that and whatnot. So we're trying to build off of each other's data. And it is suggested that 15 widely displaced stations are actually needed to validate a global climate model. However, we do know how expensive they are. We have to consider data volume and all that jazz. So how do we solve this problem? And that leads to MAPLE. MAPLE is the Mars Atmospheric Panoramic Camera and Laser Experiment. It consists of a panoramic camera and 3 monochromatic lasers, as you can see in that image there. And the goal is to basically make a small, low-powered meteorological station using optics that can minimize constraints, but maximizing science return. And we're trying to see what has been done on previous Martian surface missions and kind of see what we can already do there and try to apply it with MAPLE. So building on previous surface missions, basically every mission that has landed on the surface of Mars has seen aerosol activity between clouds, dust lifting, and even dust devils. So there is activity that can be viewed from the surface using imagery. Specifically the Phoenix mission, which was Canada had a lot to do with this mission, and specifically the lidar. And my supervisor was able to carry out 4 experiments utilizing their camera, the SSI, and lidar to measure aerosol properties. However, it's actually difficult to use this instrument simultaneously as they aren't together. The SSI is a small field of view, so you have to really focus to get that lidar in the image. And I have a nice GIF here where you can actually see the twinkling of the aerosols within the lidar itself, and that's kind of what we're trying to mimic with MAPLE. The Curiosity mission, which as Haley mentioned, I have a large part in, has a lot of atmospheric movies that tie into aerosol studies. For example, the Zenith movie, which looks directly above the rover, can measure opacity, wind direction, and angular wind speed. And the Super Horizon movie, which more points towards the crater rim, can also measure opacity and wind direction and also shows that morphology of the clouds. And these 2 movies are often paired together in the morning or even in the afternoon to try to classify cloud properties throughout a solar or a Martian day. I will also mention that these movies have 8 frames in them taken over a period of time so that we can see motion. And that if you notice that the images are a little grainy, that's because we are applying the mean frame subtraction technique, which pulls out any changes within the movie, as unfortunately clouds on Mars are very thin. And this is usually the only way that we can see the clouds through Curiosity's images. Moving on to 2 observations that are actually done only in the cloudy season on Mars. And we just completed our 3rd Mars year of data with these 2. The phase function sky survey, which basically uses 9 pointings and 3 images at each pointing to create this dome around the rover to try to determine ice crystal shape based on how the sun travels through the atmosphere at that pointing. And then lastly, the cloud altitude observation, which takes 2 movies and tries to determine altitude based on how fast the shadows are moving in the bottom movie compared to how they're moving in the top movie. Now, lastly, I will mention the line of sight, which is more of a dust observation with Curiosity, and it was actually great for us to capture the Mars Year 34 global dust storm, which you can see in this movie here. You can see how opaque the ground gets when the global dust storm is coming in, and perhaps this is very important for future Mars exploration with humans. As you can see, it does get quite thick. And this is basically taking dust, trying to find dust concentration within the crater by looking at the bottom, the surface, the crater rim, and the sky. And it is only a single image. So putting it all together based on just these two missions, we know that Phoenix has its limitations with a small camera field of view and a higher operational complexity. And even though with Curiosity, we do have a larger field of view, 45 degrees versus the 13.5 degrees, that also creates data volume concerns as all of these images come to us first, downlink to Earth, and then we process them. So we're going to try to figure out how to minimize that constraint as well. And you can see that we have a lot of science output from just imagery, which is very important and can create almost a simple meteorological station, Maple. So improvements that we've done here, I mentioned the field of view of the camera. So we're going to use a panoramic camera as that will be able to capture the whole sky. We're going to have multiple lasers rather than a single wavelength to try to characterize more particle scattering and particle size distribution. And as I mentioned with data volume concerns, we are creating an algorithm that can hopefully return data numbers rather than imagery and save a lot of data volume concerns there. And so our next question with Maple is, are we able to replicate the science returned by Phoenix and Curiosity? So we have a 3-phase plan for Maple. We are actually currently in phase 1, about to move into phase 2. Right now, we're doing instrument construction, lab testing, and local verification with the environment. And as you can see in this image here, that is kind of how a panoramic camera or a panoramic image would look with the Maple camera. And you can see the nice clouds here. Luckily on Earth, we have a lot thicker clouds, so it's a lot easier to see them in these images. And lab testing really includes this aquarium, which I personally spray painted black to try to minimize outside light coming in, and basically fill it with water, shine the laser through it, and see if we're able to get any kind of particle sizes or any information back from the laser. The algorithm that I was mentioning, I have published a paper in 2021 about this, taking the atmospheric movies from MSL and trying to apply a machine learning algorithm to determine wind direction and angular wind speed. There is some testing that needs to be done more with this. As you can see in the movies, if there are cloud decks, lighting effects, or camera artifacts, the algorithm really struggles. But if there are nice clear features, you can see the arrow is pointing directly where the clouds are moving towards, which would be the wind direction. So that's a great start. For phase 2, we are actually aiming for this spring, upcoming spring. So I'm currently in contact with a group that can hopefully help us get to Argentia in Newfoundland. Now, the reason we are choosing this area is we want an aerosol-rich environment, so thicker clouds and larger aerosol sizes to try to test line of sight and the lasers. And this will be non-remote operations, so I will be there testing Maple to see how it does in these thicker conditions. Lastly, phase 3, which we're aiming for next winter, will take Maple up to the Arctic, where we have this, what is considered diamond dust, or very fine water ice particles in the atmosphere, which is very similar to Martian-like environment. And this will most likely be remote operations with Maple as testing what it would be like on Mars. So from here, I'll say thank you for coming to my talk. Maple, the Mars Atmospheric Panoramic Camera and Laser Experiment, hopes to minimize mission costs for maximized science return and considers what we've already learned from previous Mars missions with a 3-phase plan, including lab testing and 2 field test sites, Newfoundland and the Arctic. I'm happy to take any questions.
I suppose if there are no questions for Charissa. No. Well, thank you again, Charissa, for the wonderful presentation. Sorry, I was muted. I was like speaking. But thank you, Carissa, for the wonderful presentation. And if there are no questions, I will pass it on to Jahanvi to introduce our next and final speaker, Joshua Hedgepeth.
Hi everyone, I'm Jahanvi. I have the pleasure of introducing my lab mate and my Titan buddy, Josh Hedgepeth. He did his undergrad at Georgia Tech, and then he came to Western University to work with Dr. Catherine Niche for his master's studying impact craters on Titan. And he is now doing his PhD in his final year, studying melt sheets on Titan. His paper about the study was recently published in the Planetary Science Journal. So if you're interested, I'm sure Josh can provide a link in the chat perhaps towards the end. Today he'll be talking about the distribution of organics and impact melt on Titan and how his work relates to NASA's Dragonfly mission, which he's a student member on. Take it away, Josh.
Thank you so much, Jahanvi, for the introduction. So as you said, my name is Josh Hedgepeth. I am in my final year at Western, and I'll be finishing in August. So this is some of my most up-to-date work, which was just recently published at Planetary Science Journal. So I'm going to talk about the distribution of organics and impact melt on Titan, which I know sounds very specific. So let me give you a bit of background before I get into the details. So for those of you who aren't familiar with Titan, it is unique for a few reasons. First off, it's an icy moon, which means it's a big ball of ice with a liquid ocean deep below that ice layer. But it's unique not just because it's ice, it's also really big, but it's also got a really unique atmosphere, which other icy moons do not have. This moon, this atmosphere is composed mostly of methane and nitrogen, CH4 and N2. And over time, it gets bombarded with, those particles get bombarded with cosmic solar radiation, and that causes these molecules to break apart into individual atoms. So that means you have like a mixture of carbon, hydrogen, and nitrogen just floating around. And over time, it allows for longer chain molecules to sort of get stitched together and form over time. Things like benzene, HCN, and other types of heavier organics. Central among these heavy organics are these really long-chained molecules of a bunch of different carbon and nitrogen, hydrogen linked together called tholins. These were first introduced by Sagan and others when they were trying to reproduce the early Earth, the origin of life type of scenario, where you get this chemistry which isn't quite life, but it's considered prebiotic because of its potential to evolve into something akin to life as we know it. So that, when you think about it, when we talk about things that life as we know it, basically these tholins, when mixed with water, liquid water, or introduced to oxygen in some way, liquid water is just one way, it will begin to oxygenate, which means you're going to have a new molecule formed, which basically latches onto that oxygen, and you might end up with something like what's listed here, which is an example of an amino acid. Amino acids, nucleobases, these are all things that are foundational to life as we know it, and they're forming almost certainly on Titan in some capacity. That means that Titan is a natural laboratory that's been going on for millions of years. And that is the motivation, of course, for Dragonfly. This mission that we're sending, NASA is sending to Titan in the late 2020s, arriving in the 2030s, to investigate its geology and its astrobiological potential, particularly understanding the origin of life and how we can understand that transition from this prebiotic molecules that exist on Titan and likely on the early Earth to the biomolecules that compose life as we know it. And what's cool about it is we're sitting this quadcopter, which is a lot like a rover you would see on Mars, but because Titan is so unique and its environment is so unique, it's able to send a quadcopter the size of a traditional rover that can traverse for kilometer spaces and investigate on a whole new level, get whole new perspectives that you couldn't get in a scenario like, say, on Mars. So they're investigating a lot of different things on Titan, but one of the places that they end up or aiming to go to in the final stages of the mission is going to be Salt Crater, which is a impact crater that exists along the equatorial region of Titan. The reason I care about this is for a few reasons. The equatorial region is known for having these very dense or this large amount of sand dunes, these little black streaks, are known as organic sand dunes. And when we don't know exactly what they're composed of, there's strong reason to suggest that they're probably composed of the very type of organics that we observed in the atmosphere. So these tholins and other type of heavy organics that we're interested in exist on the surface in very large amounts. And when you think about an impact crater, when it forms, all that energy gets bombarded into the surface. Things get moved, but some things get vaporized and melted. So you're left behind with a thin melt sheet. These melt sheets, while geologically thin, could survive for at least tens, likely even hundreds of thousands of years, depending on the type of scenario we're talking about. These estimates will depend on how thick it is, which will depend, of course, on drainage and how big the crater is. Selk is a pretty decently large crater, 80 kilometers, which is why they're going there. But what I'm interested in is this bigger question. Okay, you want to get these samples, you want to get these tholins, these potential biomolecules that could have formed in this melt sheet after the impact crater formed, because there is going to be some mixing, which we've done estimates on. I talk about it in my paper. And if that's the case, it's not as if you can just get a spoon and get out the material you want. You're going to have to get a sample. You have to get into the ice. It's going to be refrozen. And it's not just a question of how deep can you get, which is a more complicated question, but it's a question of if you could get any sample you wanted, where would you want to sample it from and why? And what I'm trying to get at here is, how do we know how things are going to get placed in the ice? The ice is going to be like a compartment, like a refrigerator that is storing all this information. We would need to know how it is basically sorting everything through time. These are two important things to understand: the amount of material that's freezing at any point along the melt sheet, and the times it experienced in a liquid phase. When we talk about the origin of life, time is very important, because the time it takes to create life, while it's unknown, more time tends to be a good thing, more time for chemistry to evolve. So if we can constrain the amount of material that's freezing at any point in the melt sheet and the timescales, we can begin to get a much better understanding of what sample we're getting. That's important context for any sample we get, but also if they have a choice in where they sample, this will also help guide them in the direction where to go. So what we did here then is we basically tried to study this from a sea ice model perspective. So the slush fund 2 model is basically a sea ice model that is a compendium of other different types of models that have been used to study sea ice on Earth. It was originally created using the mushy layer theory. This is specifically, it's basically this idea of the region where ice and water, the ocean, is meeting with the ice, is going to be mushy. It's not solid, it's not liquid, it's in between. And it's in that region where most of the physics that's controlling the emplacement of material impurities that's going to happen. But you also have other things like gravity drainage, which is what's driving stuff to move around. And the enthalpy approach is just a way of constraining a change in phase. And what I want to stress here is that we're basically taking a model that has been used in a terrestrial scenario and designed in a way to sort of constrain it in a way that we understand the physics fairly well, and then apply it to new scenarios where the physics should be different. Here we see on the right an example of a chaos region forming under or above a melt lens that could have formed on Europa. And this is a good example of how this model can be applied to a scenario that seems very different than Earth, but also is very similar to Titan as well. So you have the ocean here at the bottom, which is similar to what we see on Earth. The melt lens, while it might be inside of here, is actually going to be very similar to a melt lens on Titan, where instead of being enclosed in the ice, on Titan is going to be exposed to the atmosphere. But the physics that's controlling the process of how the material gets trapped in the ice or moved is going to be the same. So I just want to stress that to understand that the physics that we use to understand Earth can be used here. And I don't want you to have to understand these. There's a lot of different numbers. The main takeaway here is these are conservation equations and the convection equations. Basically, we need to control the change in mass, change in temperature, change in volume, which if you have a change of phase in water, the volume is going to change, and then a change in the concentration of the impurities. And the thing about this is that all of these properties, all of these physical parameters are intersected. So it requires this more complex physics to understand how they're all evolving, how one affects the other. But then fundamental to that is what is driving these things to change. As the water is freezing, why doesn't everything just stay where it's at? And the driving factor here is, in fact, gravity, basically density differences between the water and its impurity. That's what's driving this entire process. So to jump straight into the results that we found for HCN essentially is what you see here. So what I'm showing here is, imagine you could go to this melt sheet and you got like a sample that you took throughout the entire depth of it. You have like a cylinder of ice and you measure how much is in that section of it at any particular depth. That's what you're looking at here. Some amount of stuff frozen in the ice at some depth. That is going to vary depending on how much material you start with, which again, we talk about those initial estimates in my paper. This is just to show you a variety of things. It's the main pattern that matters here. And while there's a lot I could say about it, the main thing I want you to understand here is look how things are so much higher in the upper fraction of this melt sheet, so much lower on the bottom. This is because if we think back to the gravity portion here, HCN happens to be more buoyant than water, which means the buoyancy of HCN will cause it to be held in place as the ice lattice is forming on the upper boundary of this melt sheet. But as the base of the melt sheet continues to freeze, because remember, Titan is cold all around, not just on top, it means that the buoyancy will want to drive it out as it's forming. So the physics that I just showed you, that these complicated equations here, they're controlling this base model here, this base portion. And as stuff gets rejected down here, you can actually see a slight increase in the top. So things are just sort of feeding back into it. But this was just some initial estimates, like a first order approximation, because HCN, we studied it because it's something we know exists in high amounts on Titan. And we also know that it will begin to form a biomolecule, things like amino acids and nucleobases when it begins to hydrolyze in water. It's not a tholene, strictly speaking, but it has the same sort of idea behind it. But this first order approximation is not necessarily a great one, because HCN, one, won't be the only chemistry, and two, it's going to be actively changing. And when you have a variety of chemistry or chemistry that's changing, that means the chemical properties that are controlling this entire process is going to change. So now I want to talk about a potential biomolecule, a glycine, an amino acid, that was the next thing we're beginning to study. And I want to study this for a few reasons. One, just to show you what an amino acid might look like, how it's the same general idea. The difference here is it's inverted. You have a lot more freezing on the bottom and the top. And maybe you can guess why. It's because glycine is denser than water. So you get this inverted scenario. And while we still have this problem of glycine isn't the only molecule that will exist, the point here is to show you the two different sort of endpoints, the two types of extremes we can expect to find. When material is more buoyant, the impurities are more buoyant, going to freeze at the top, or they're going to be more dense, they're going to freeze at the bottom. The complicated thing here is that these patterns we're showing you, they can evolve with time, because if, say we start out with a bunch of molecules in a melt sheet, and over time, they evolve from being really, on average, denser than water to being more buoyant than water. That means you could see a pattern like this where they get inverted in the interior of the melt sheet. And I know there's a lot taken here, and I'm not trying to get you to understand like all the finer parts of what we're trying to understand here. What I wanted to show you was the complexities that go into trying to constrain this process, and all the factors that can cause these patterns to be much more complicated than these first order approximations. And a lot of it is something that we can begin to understand just by comparing the two. Glycine as a daughter product, we can begin to estimate at which point will we expect HCN to turn into glycine by using these sort of timetables that I made using HCN. Basically, if you have a melt sheet of a certain thickness, its top and bottom will begin to freeze, and I sort of get an estimate of how long that takes. For a 10-meter melt sheet, you can see it starts to freeze quicker on the top versus the bottom because it's exposed to the atmosphere. And the point is that you can track through time. And this is relevant because hydrolysis we have rates for. So the amount of time it takes for HCN to evolve into glycine or any other daughter product is something we can measure. And the estimates are that depending on the conditions, it could happen in a matter of, it could evolve, have a half-life of a few weeks to 100 years. Half-life being basically how long it takes for half of that HCN to evolve into its daughter product. And what we can do here is we're going to say that at least for 100 meters or thicker, at some point in the melt sheet, you will begin to see the daughter product begin to dominate the mixture. Like in this situation, it's simple because we go from HCN to glycine, we know they're fundamentally different. And if we think of it that way, we can say that at some point, this glycine profile will be more applicable than HCN. And that point is going to be for 100 meters and deeper of melt sheets. And again, I know it's a lot to take in. The main takeaway here is more buoyant things will freeze more at the top, denser stuff will freeze at the bottom. The way in which this happens for a mixture is more complicated, and especially when that mixture is actively changing. Future laboratory work, though, is something that we're hoping to do because it'll help us understand, I guess, the rate of hydrolysis, but also the way in which mixtures interact with each other in this process. Thank you so much for your time.
Awesome. Thanks for the presentation, Josh. Does anybody have any questions for Josh? Yes. Any questions? Going once? Going twice? Okay, well, I guess we can conclude here. So thanks again, everyone, for dropping by. Thank you to the trainees for their presentations. And we'll see you all at our next TEPS seminar, which will be on April 13th next month. So thanks all for coming, and we'll see you then. Take care and bye-bye.